Okay. Conversions. Signals come into PLCs as 4 to 20 milliamps. Inside the PLC, in this case I've got a 15-bit ADC. Inside the PLC, it's converted into counts. These are counts. Now, it would be really, really nice if 4 milliamps was converted into 0 counts. And it would be really, really nice if 20 milliamps was converted into 32767. 32767 is the biggest number I can have with a 15-bit ADC. So it'd be nice if 4 milliamps was 0 and 32767 was 20 milliamps. That would be nice. Unfortunately, that is not what most PLC manufacturers do. This is what most PLC manufacturers do. 0 milliamps is 0 counts, which means 4 milliamps is 6553 counts, and 20 milliamps is 32767 counts, which means that if you want to know what 12 milliamps is, it's, well, goodness knows what. It's a horrible thing to work out. So it's, well, it's a bit complicated. Whenever we can, instead of setting up the ADC input to be raw counts, this is raw counts at the moment, we set the ADC input up to be percentage. So we set it up as a percentage input. What that means is 4 milliamps is stored as 0 counts. I'll just get rid of that because it's not relevant anymore. 4 milliamps is stored as 0 counts, and 20 milliamps is stored at 10,000 counts. Now 10,000, if you remember from last week, 10,000 scaled integer, actually means 100.00. So 10,000 as a scaled integer actually means 100.00%. So if we set our ADCs, our analog to digital converters, as percentage input, we get a usable number. We get something we can deal with. And we know that, say, 12 milliamps will be 50%. So it's dealable with. Whereas raw counts is something that just makes your head explode. Okay, now we've finished the first half of this evening. I would like to take a 5-minute break now. So I'm going to start the clock. In fact, I'll take a 6-minute break now. So we'll take a 6-minute toilet break, and I'll see you in a moment. The second half of the thing I want to talk to you tonight about is programming structure. This is how we write programs. Now, there's two sides to this. There's the writing of the program, and then there's the maintenance of the program, or the fixing of it, fault finding. Now, I've been an installer, and I've been a maintenance person. And I know what it's like to do both things. The installer just wants to get it done as quickly as possible and get out of there. The maintenance person, on the other hand, hates the installer. because he has to maintain it. He's got to be there for long term. So what I'm going to concentrate on is trying to teach you to write programs that are good for the maintenance person. And that might mean there's a little bit more work for the installer. But actually, it's a small price because it works out better in the end. So let's go into this. Now, to demonstrate this, I'm going to use a very simple program. What's happened is an engineer has given me this specification. So I've got this spec. And he said, this is how I want you to control, it's a building. It's my classroom at TAFE. My classroom at TAFE and the grass area just outside. So he said, right, in the summer, when it's hot, I want you to turn the cooling on. In the winter, when it's cold, I want you to turn the heating on. In the summer, when it's late evening, I want you to turn the outside lights on. So these are the outside lights. When it's winter and it's early evening, I want you to turn the outside lights on. In the summer, if it's early morning, I want you to turn the reticulation on. And whenever it's daytime, which means whenever it's between 9 and 5, I want you to turn the air compressors on. So that's my specification. Now I come along with my PLC and I start programming. And this is the program I write. It's called a serial program. It's ladder logic. Hopefully most of you are familiar with ladder logic. It looks very similar to relay logic. It's serial programming because all I've done, serial just means one thing after another. What I've done here is I've taken one problem after another and written a line of program to fix it or to do it. So I've gone, when it's summer and it's hot, turn on the cooling relay. When it's not summer, in other words it's winter, and it's cold, turn on the heating relay. When it's summer and the late evening switch comes on, turn the outside lights on. When it's not summer, when it's winter and it's early evening, turn the outside lights on. When it's summer and it's early morning, turn on the reticulation. When it's daytime, turn on the compressors. Okay, this is a ladder logic program. It's written for the Allen Bradley, which is, well, it's one of the worst PLCs I've ever worked on, to be honest. But anyway, this is a ladder logic program then. How many of you are happy and have seen ladder logic before? Okay, that's good. Now here's my problem. I'm the maintenance guy. I've come along 2 years later and I upload the program from the PLC because the laptop that the program was written on has long since disappeared. Now when you upload from the PLC, quite often you don't have any comments anymore. So I'm looking at a program that looks like this. I've got no comments. I don't know what any of it does. And I'm trying to fault find it. Now, I've now got the problem, I don't know what any of this stuff does. So I've got to go through and I've got to look at it and say, all right, that's input 1. When input 1 is on and input 3 is on, output 1 comes on. Okay, I have no idea what any of that means. So I've got to go off and pull out the wiring diagram. Hopefully I've got a wiring diagram. And I go and find out, oh yeah, input 1 is connected to screw number 374, and I start tracing that back and find that input 1 does this, and input 3 does that, and that output 1 does that. Okay, so I know what that line does. Now I've got to go to the next line and work out what this input does and what this input does, and work out which one of these is outputs. Because I'm trying to fault find this, I'm trying to find out why the retic didn't come on. And I'm going to have to work through this line by line. And if there were 400 lines, I would have to work through 400 lines before I got to the one which happens to be down here, which is the retic. So, fault finding wise, this is a nightmare. So I really don't like this type of programming. It doesn't tell me what's going on. Now, in its favor, what you do with serial programming is, it's serial, one thing after another. You fix each problem line by line. In its favor, you start at the beginning and you work through, which is the natural way of doing things. It's the way you've been taught to do things since you were an apprentice. Start at the beginning and work through. Against it, if there were 400 things in the original spec, there would be 400 lines in the program. They're not necessarily in any logical order. They're just in the order you happen to have done them. So it's a nightmare to do any fault finding on, especially if you don't have any comments. To get round this problem, round about the 1970s, people decided that the thing you should do, so this is the 1970s. You've got to remember back to the 1970s, those of you that were alive then. It was the tail end of the Vietnam War. People were wearing funny shirts with big collars and high-heeled trousers. All sorts of strange things. The 1970s was the decade that taste forgot. So, round about the 1970s, they decided the way we should organize programs was to use a thing called the flow chart. With a flow chart, you would have a start, and then you would have diamonds, which were decisions. A diamond is a decision. So you'd have these decisions, which would be diamonds, and there'd be decisions like, is it summertime? No, it's not. If it's not, go over here. If it is, go down there. So let's say, oh yes, it is summertime. Then we go to the next decision. Is the temperature high? No, it's not. We'll go to the next decision. Or, yes, it is. Go off and turn the cooling on. See, rectangles are where we do actions. We actually make outputs or actually do things. So, yes, the temperature is high and it is summer, so we need to turn the cooling on. And then having finished turning the cooling on, we jump to over here. And then we say, going down this line, is it late evening? Yes, it is. Then turn the lights on and jump over here. Or, no, it isn't, and follow down that line. Is it early morning? Yes, it is. Turn the retic on. Then jump down here. And then jump back to the beginning. And we're back through, going down this decision line. Or we may have made a decision right at the beginning and decided that it's not summer, it's winter, in which case we're going to turn the heating on. Or it's early evening, in which case we're going to turn the lights on. Now, this was the way we had to do programming in the 1970s. You had to. It was a rule. Okay, to implement this, what we would do is we would do lots of jumps. So implementing programming flowcharts using ladder, we would do jumps. So you'd have these things here. Is it summer? If it is summer, if it's not summer, jump to label 1. So label 1 is down here. So if it's not summer, we jump past all of these lines, we jump from here straight down to here. And then we do these things. We do that, we say, all right, is the temperature low? Turn the heating on. Is it late evening? Turn the lights on. Then we've got another label called daytime, and we've got another label called label 2. We turn the compressor on. Is it daytime? Turn the compressor on. And because it's ladder, we immediately jump back to the top again. Now, if this had been false, then we wouldn't have jumped to label 1. What we would have done instead is said, is the temperature high? Because we're doing the summertime stuff. So what we have here is we have from here to here, that's the summer stuff. And then from here to here, that's the winter stuff. So we're saying at the beginning, is it winter? If it is winter, jump off and do the winter stuff. If it's not, continue down and do the summer stuff. Then when you finish doing the summer stuff, jump to label 2. So off it goes and jumps to label 2, which is just there. And then it does its label 2 stuff, and it comes back. It's all good. Now, that's all well and good, but there's a slight possibility of problems with it. If I make one single typing mistake, if I make a typing error, and instead of writing jump to label, instead of just here, where it says jump to label 1, if instead of doing that, I put in label 2, then what it's going to do is it's going to come along and do that line and jump to label 2, which is down there. And then it's going to do that label 2 line, which is checking to see if it's daytime and turning the compressor on. And then because it's ladder, it jumps back. And then it does that line, which is jump to label 2. So it'll go back and check the compressor. And then it will jump back. And then it will jump back and check the compressor. And then it will jump back. And the problem I have now is it's not doing any of the other rungs. And in here I could have the rung which says go off and check the nuclear reactor temperature, or go off and check the warheads haven't set off. So what we've got here is a thing called an infinite loop. An infinite loop is where it goes off and just does a few little rungs of code and misses all the rest. And infinite loops are caused by a typing error. Somebody typed in the wrong label. It's a very simple thing to happen. Happens all the time. So, in its favor, a flowchart, it organizes the program. It gets everything organized. Against it, for a start, it's very difficult to fault find. Effectively, all these jumps from here to there to the other place, it's a bit like snakes and ladders. With snakes and ladders, you've got the things that you can go up, and then you've got the snakes which can bring you down, and you've got the ladders which can take you up. Now the problem with snakes and ladders is if you get to number 27 in snakes and ladders, you can't tell how you got there. You can't tell which route you took to get to number 27 because there's lots of jumps everywhere. You can't tell if you went down 2 snakes and up 3 ladders or if you just went there directly. So it's difficult to trace when there's a fault because you can't tell what led up to that fault. It's what we call spaghetti programming because it's jumping from here to there to the other place. If you've got a big program with, say, 400 lines, and you start going through it, and you say, all right, jump to label 3, and you go off to label 3, and you read and do this, do that, do that. Oh, jump to label 7, you go off to label 7, and you does that, does. Jump to label 19, you go to label 19, jump to label 14, jump to label, and you're thinking, I've completely forgotten what it was I'm looking up. Because you're jumping backwards and forwards so much, you just lose track of what you're doing. So it's very difficult to fault find. Spaghetti programming, it just jumps, it's just like a bowl full of spaghetti. But the biggest possibility, the biggest worry of all about this type of programming is that there's a possibility of an infinite loop. There's a serious possibility of an infinite loop. And if you get an infinite loop, it will go off and it will just continuously check the reticulation while the nuclear reactor overheats and the warheads fire off, because they're not being checked. So infinite loops, they're not just a possibility of an infinite loop, it's a probability of an infinite loop. If you write a program with 200 labels, you're going to get one of them wrong. And then you're going to have an infinite loop, and then it's going to disappear up its own bum, basically. So it's a very dangerous system. So the rule came out around about the 1990s that you must never, 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 ever use flowcharting, because flowcharting leads to labels and jumps, and labels and jumps lead to infinite loops, and infinite loops leads to things blowing up. So you must never use flowcharting. Unfortunately, most of the lecturers you'll meet learned to use flowcharting back in the 1970s and are still teaching it. So it's a completely discredited method, and you really shouldn't be using it. What we should be using instead is a